So this is the Phase 2 Team 7 presentation. For our design, our main mission objective was to design a device that can perform inspections and repairs inside confined spaces. The main objectives for this device are to be able to perform visual inspections, UT testing, eddy current testing, and remove and repair fasteners. So our main goals by the end of this phase were to be able to finalize drone and subsystem design, determine physical parameters, create multiple diverse designs for different subsystems, and identify the critical loading. For our design, we decided to create a drone that you can attach the different testing kits to the bottom. The front legs will be able to pivot out and connect to the wall that it's going to be attaching to, and then rotate itself down underneath until the kit is level with the surface. And then at that point, the kit will be able to run its test against the wall and then deattach itself and return back to the operator.
Our revisions from phase 1, we've decided to go with a different base model for the drone. The new model we selected removed a lot of the cosmetic parts that the first drone had, so that reduced the overall weight, and the new design is also much simpler and easier to modify. We've also decided to use some aftermarket parts on our drone, such as a larger battery to increase the flight time, as well as different motors to provide more thrust. And we've also decided to use a signal repeater to eliminate the need for an umbilical cord. For the actual model of the drone, the body is based off a Lumineer QAV250. It's a very lightweight frame made of carbon fiber and aluminum that weighs just over 0.8 pounds. And it has, these arm links are modular, so they can be changed out to accommodate smaller or larger propellers if needed. The motors are very lightweight. They weigh about an ounce each, and they can provide 1.8 kilograms of thrust. They're rated for harsh and unstable environments, so they're brushless motors. They won't produce sparks to interfere with a volatile environment, and they're also waterproof, so any humidity or moisture should not affect them. And they're mounted to the arms through 4 screws on the bottom. The other components we've mostly left stock, such as the electronic speed controllers, the flight control board, transmitter, and blades. On the blades, we have seen that a 3-bladed prop could be used to possibly increase the thrust. But so far, the combined weight of the other electronic components is about 0.4 pounds, and that they should not produce any considerable power draw that would affect the flight time of the drone. For the configuration we have now, the total weight of the drone with a battery is 5.6 pounds, and that will give us an additional payload of 4.3 pounds we can carry. With the maximum payload, we should have a flight time of 20.4 minutes, but we don't expect to be operating at that max weight, so the flight time should be considerably longer than that. The battery we have currently selected, it weighs 4.1 pounds and it has an energy capacity of 1400 milliamp hours. There are many different batteries we could choose. It's finding a balance between a larger battery and the flight time. So a larger battery would take up more of the payload but give us a longer flight time, or a smaller battery would give us shorter flight time but give us more extra payload. For the legs on the drone, they weigh 1.1 ounces each, and they'll be driven, the front legs will be driven by a gear and motor assembly to pivot upwards. The controller we've selected has multiple different display screens and programmable buttons and functions, and it can also be interfaced with a laptop to provide extra control, such as for controlling the subsystem kits. And we've also decided to use a signal transmitter that will be inserted just inside the access port of the confined space to bounce the signal from the operator to the drone.
So for the kits that we'll be attaching to the drone, for the ultrasonic and the eddy current kits will be universal. The only difference is a switch out of probes. So the kit will be attached to the drone via a track mount. The whole function of it's more like a claw machine. So there'll be 2 rods that you see here and here that will be one track that moves it widthwise across the drone. And then there is a screw slider that is attached to another motor that will move it forward and back. And then there's a second motor that will drop the probe down. Then for the UT kit, there will also be a bag of conduit that will then be pumped. It will be pressurized, so when we release a valve, it will release a small bit of gel so that the actual UT testing can be performed. For the eddy current kit, there will not be that there. It'll just be the probe.
Okay, for the next subsystems, we choose the pulse detector probes for the eddy current and the ultrasonic. So in this case, we got Bluetooth and Wi-Fi technologies equipped, and the total weights are 0.437 pounds, and the dimensions are so tiny that we can handle it on the box kit. And also the range and resolution are good enough to measure or to know if we got some cracks over the surface. For making work the eddy current and the UT systems, we got 4 options. The first one would be just the probes attached to the drone, but that wouldn't allow our team to move the probes over the surface. Then the second option is having a mechanical arm with a 360 degrees freedom. So in this case, the actuator is capable to move over the surface. But then we come into a third option, that it's a kit box housing. So in this way, we got a track mounted over the drone, and also it's capable to hold all the testing systems. But then we got a fourth option. In this case, we are using a coolant that it's that will introduce some gel into the surface, so the UT testing can be run.
This drone to the wall that it's going to be working on, we decided to go with the suction cup technology. These suction cups, as well as being able to hold the drone to the wall, will also serve as landing pads whenever it's not in use. We're going to be using 4 different suction cups that are both 30 millimeters in diameter. Each cup can provide 32 newtons of force, which will be more than enough to hold the drone to the surface while it's running the tests. To power these, we're going to be using a micro diaphragm pump that will be small enough to fit on the drone and light enough to not cause very much payload increase, as well as be able to provide 90 kilopascals of suction force, which would be sufficient.
For the optics portion of this project, we've decided to just go with the camera that's already mounted on the drone. That way we're not having to mount an additional camera that's just bulkier and will weigh down the drone, and then also it prevents someone from having to physically get inside the space to locate the faulty rivets. We've decided to go this route because it's easier to use, it's already mounted on there, and we can make it work. The way it'll work is the drone will fly into the cavity, taking a long video to capture every surface, and then the video will then be loaded into a photogrammetry software that will locate the position of the faulty rivets. The way the software works is it compares the common areas of each frame of the video to essentially make a map, and then it can figure out where exactly each rivet is located that we're trying to fix. A couple potential issues are just crashing the drone or slow computing time, because the software that will be used is pretty computer intensive. For this project, we have quite a few major concerns. Our first major concern is drone thrust. A few options that we have to increase the thrust of our drone is we could possibly add extra motors, we could adjust the prop, and we can reduce the weight. When the drone is flying inside the confined spaces, one of our biggest issues is going to be signal loss, because the signal can't really travel through the metal shell as well. Couple ways we could combat this is we can run an umbilical cord, so the drone will be towing a wire, or we can add a signal repeater right inside the access hole. The next major concern of ours is that the front leg's not holding the weight of the drone. We could combat this by using stronger, more expensive material, increasing diameter of the legs, or have suction line on the outside of the legs. There's also a concern with crashing it, because I don't know about you, but I've crashed a couple drones. I'm assuming everyone crashes one their first time around, so that's obviously one of our concerns. So one way we're going to combat this issue is we could possibly choose a different antenna that doesn't stick up as high. We could add shrouds around the blades, and we could set up a system where the motors automatically turn off if it senses suction loss.
So for our critical stress locations, our major concern is the front legs, mainly in the hinge area. So when the drone rotates down, all the force is being acting pretty much through the centroid of the drone. And so it's going to cause very weird angles and weird stress distributions. And so we're going to have to do a lot of calculations there. We're also worried about the front legs suction, just because of, again, the weird angles is not going to be perpendicular to the wall, all the forces on it. The other concern would be fatigue in just the constant loading and unloading of the track mounts. And then we do have some worries with the sliding screw stripping out, just if something gets caught on something, or the top motor, the gears wearing out.